century space launch objectives. A new universal flame deflector and trench will be completed in early 2015 and will support the new Space Launch System rocket and possibly a variety of commercial launch vehicles. For more than a year, NASA's Crawler Transporter, CT-2, has been undergoing a major tune-up in KSC's Vehicle Assembly Building. The crawler modifications are designed to enable the vehicle to transport heavier launch vehicles, including SLS, to the pad. Once the roller bearing work on half the crawler is completed, it will be prepared for a test rollout scheduled for January 2014. After traveling 3,600 miles above the Earth during the Exploration Flight Test 1 mission in September 2014, Orion will splash down in the Pacific Ocean, where it will be recovered with the help of the United States Navy. In August, with the Navy's USS Arlington stationed against its pier in Virginia, divers in small boats led the test capsule to the flooded well deck of the ship. With the capsule in position over the recovery cradle, the water drained until the capsule settled. Navy divers prepared for the recovery test in Norfolk by training in the 6.2 million gallon pool at NASA's Neutral Buoyancy Lab near the Johnson Space Center in Houston. In July, the Orion team successfully conducted the Parachute Test Vehicle PTV-5 airdrop test at the U.S. Army's Yuma Proving Ground. 17 parachutes were deployed during this test. 9 were test technique related and 8 were the Orion system parachutes. At the Operations and Checkout Building High Bay at the Kennedy Space Center, the Orion team completed hundreds of welds and installations for the spacecraft's propulsion, life support, and environmental control systems. At the Johnson Space Center in Houston, NASA Administrator Charles Bolden welcomed 8 new astronaut candidates. This group will be among those who may carry out the first ever human missions to an asteroid and onto Mars. In October, recorded Orion telemetry was successfully transmitted between the Mission Control Center in Houston and the White Sands Communication Facility in New Mexico. White Sands will be used during the EFT-1 flight to receive and retransmit the Orion spacecraft telemetry. In late September, NASA astronauts Rick Linehan and Mike Foreman tried out a prototype display and control system inside an Orion spacecraft mock-up at Johnson Space Center during an Orion ascent simulation. Over the course of 2 weeks, 10 crews of 2 astronauts each performed launch and abort simulations inside the Orion mock-up to fine-tune the design of the displays and controls.
"2014 is off to an amazing start as NASA rockets towards this year's launch of Exploration Flight Test 1. The Orion program began the year with several major milestones. The service module was completely finished in January at Kennedy Space Center in Florida. The service module is the part of the spacecraft that contains all of the structural elements, spacecraft adapter, payload fairings, and crew module separation systems the EFT-1 capsule needs to conduct its high-altitude orbital testing. In February, the completed service module was stress tested for the final time. The structural loads test proved that the vehicle will endure the physical stresses of its upcoming flight. After the test, the service module was ready to attach to the crew module. A test of the forward bay cover and parachute system was successfully passed in January at the Yuma Proving Ground in Arizona. After the Orion mock-up was dropped from a plane, the forward bay cover separated from the capsule, allowing the parachutes to release as the crew module descended safely to the desert floor. The capsule, parachutes, and forward bay cover were recovered and subjected to additional testing in the following months. In February, The Delta Mariner delivered 2 of the core and starboard boosters for the Delta IV Heavy rocket. After the boosters go through stringent testing and processing in the Horizontal Integration Facility, they will roll out to Launch Complex 37 for EFT-1's launch later this year. A full-scale mock-up of the Orion capsule was delivered to Langley Research Center in March. The mock-up will be used to perform a variety of static and impact tests to evaluate various water landing scenarios in a wide array of different conditions. At NASA's Kennedy Space Center in Florida, upgrades and modernization of the multi-payload processing facility continue as the building is readied for Orion processing support. By April of next year, the MPPF will have updated structural elements like environmental control systems, high bay doors, and emergency systems. The facility is also upgrading spacecraft preparation elements such as fuel and breathable gas systems, time-critical installation equipment, and ground support equipment storage. In January, the Crawler Transporter 2 completed a test drive on new traction roller bearings in 2 of its truck sections. The new roller bearings are one of several upgrades to the Crawler Transporter, which will carry the significantly heavier Space Launch System out to Launch Pad 39B. The other 2 truck sections of the Crawler Transporter will also receive new roller bearings and complete a follow-up test drive in November. In February, NASA and the Navy tested procedures to be used during Orion recovery operations. After launch and re-entry simulations, the forward bay cover and parachutes were successfully retrieved from rough waters off the California coast. The ocean turbulence in the well deck of the recovery ship made it difficult to secure the Orion test article. The challenges experienced during this test reinforced the necessity of practicing spacecraft recovery. The circumferential dome weld tool produced a second liquid oxygen tank confidence article at the Michoud Assembly Facility. The confidence tank verified that the weld tool is capable of producing the core stage tank up to the exacting standards the Space Launch System will require. A composite cryotank for liquid hydrogen was also produced and delivered to Marshall Space Flight Center aboard NASA's Super Guppy cargo plane in March. The advanced composite cryotank, which could benefit many of NASA's deep space exploration spacecraft, will undergo a series of structural pressure tests later this year. A scale model of the SLS was used in acoustic testing to see what effects high and low frequency sound waves will have during launch. The model's core stage fired for 5 seconds while an array of microphones collected the acoustic data. A full assembly test with the scale rocket motors will be conducted later this year. In March, NASA Administrator Charles Bolden visited Marshall after the software integration team powered up the flight avionics, which includes hardware, software, and operating systems for Space Launch System. Known as First Light, the flight computers of the SLS simulated the flight path the vehicle will experience during launch. NASA's Exploration Systems Development Division is flying through production, testing, and launch, as 2014 promises to be one of the most productive and exciting years in recent space history.
Hey, how are you doing?
My name's Naomi Akin.
And my name's Kelly Marie Tran. And we're at NASA's Johnson Space Center.
And we're training to be astronauts.
No big deal. I'll pick to the tool. We got this.
Come on, let us do it!
Let's go.
The first thing we're going to show you this morning is what's called a gravity offload system. So
People often think that we have a room here where you can go in and flip a switch and suddenly you're floating. That's not really how it works.
You want to see how it works when you're 1/6 your weight or 3/8 your weight. We use Argos to do that. And then we use it to work on like new tools, new geology, sampling procedures. So from here, what we do is we'll lift you up off the ground.
Oh my God!
And we'll put you into lunar gravity. All right, so this right here is zero gravity. So if you're at the space station and I were to push you and say, see ya, you're just gonna put it away the way I push you.
So what did you guys think of that?
It was so cool. I was saying I realize now why astronauts walk like this.
Yeah!
Because everyone's just like trying as much as possible.
Do you guys want to go check out suits?
Yeah.
Want to go try some on? Alright. Yeah. Next.
So we're going to talk to you a little bit about spacesuits today. We're going to move some suits over here, I think, real quick, and we'll talk to you a little bit about what they are, and then we're going to let you guys change and actually try some out.
So you go out there and there's no air. So then there's pressure pushing in on your body?
So what we would have to go through is your body would want to expand out, so that's why we wear a suit around us that goes through and creates an artificial atmosphere.
Do you guys have training in terms of how quickly you can get in and out of these? Is that a thing or not?
No,
Like
I mean you have to know your
Yeah.
spacesuit really well, but we don't do drills like getting in
Yeah.
them quickly. You typically are helping each other, getting into and out of them when you're in space.
And so those tubes actually are going to carry cold water to help us cool. We'll see what that feels like once we get inside. But these guys are going to help you get climb the missions.
Yeah, like
Chewie. But the guy who plays Chewbacca.
Stand up.
Well, unfortunately, we're going to get you guys out of the suit now, but then we're going to take you over and see the vehicle that you would be in these suits in.
Okay.
In the Orion vehicle.
This is the Space Launch System. This is what's going to push this capsule. This is the Artemis 1. This is going to go to the moon about 1 year from now.
Yes.
Oh my gosh, this is
Yes.
okay. 9 and 9
This is the docking hatch up here. When we get to the gateway, we will dock at that port, and there will be a hatch up there that we open to go into
Which
the
you
gateway.
have to like target, right? So you have to like figure out a way to drive the rocket so that the holes match up.
Bingo. You know how
Right?
precise it is? First of all, relative to the Earth, we're going over 20,000 miles an hour, and when we dock, meet up with this plus or minus 1 inch, plus or minus 1 degree in each axis.
Okay,
That's really difficult.
Yeah, we actually make the switches, it's a multi-step so you don't accidentally hit a switch.
We're going to go check out the mock-ups for the space station, which will seem luxuriously large.
Okay,
This gives you an idea how big of a room each person gets, so you can put up, your personal effects.
So yeah, you do. You have a sleeping bag, as they mentioned, and you can pin that to the wall, and you can float kind of inside your sleeping bag. You can tighten it down if you would like to feel a little bit more stable.
This is Houston. Yes.
This is when they actually say Houston, we have a problem. This is Houston.
so that's live.
They're in space right now. Oh my gosh, it's mad.
What's the day-to-day like in this room? So in this room we have 3 shifts a day. My favorite shift is the night shift because it's when nobody's in this building but we get to hang out with the crew.
Are you guys ready to try some space food? That's next on the list.
Where do you get the suggestions of what to work on next?
That's a great question. We get a lot from the crew office, or the crew office says, can we move away from red meat and potatoes and get Brussels sprouts, butternut squash? And this comes from a lot of crew comments as well as input from the nutrition line here at JSC that says, you guys should probably go with the salt in here. So on station, the astronauts have a much more advanced dehydration apparatus. They have the potable water dispenser. The astronauts can help you with figuring out how to unlock the straw.
Release this. Great.
Because otherwise,
So that way when you set it down, liquid's not going to come up on out on it.
Stuff is at the bottom, so you want to like.
she knows the tricks of the trade.
Okay.
Which one is your favorite?
I would say the butternut squash is my favorite. I like things that are sweet.
I like the Brussels sprouts, I think. They're so good.
All right, well, you guys have had your afternoon snack. Now you ready to go drive a lunar rover? All right, let's go check it out.
I really don't know how to drive. This is like going to be a
Oh, what is that? Oh, is it here? Ooh, it's air conditioned. It's air conditioned? Twist. Yep.
This is so cool.
On the lunar surface, it'll basically be, you're in the rover, like Megan and Jessica will be in the rover for up to 14 days living together. And there'll be another rover, they'll go out for 14 days and explore. And if one breaks down, all 4 of you will jump in one vehicle.
I think I made contact. I think we're there.
Awesome.
We're there.
Yeah.
That was smooth.
That was awesome.
Dude, what an amazing day. It's been really good.
It's been amazing. It's more than I expected.
Yeah.
I just have so much respect for NASA. Yeah. Thank you for bringing us here.
What's up for October? A harvest moon and a blue moon. Mars is up all night, and a journey beyond the galaxy. This month brings not just 1, but 2 full moons, at the beginning and end of the month. The full moon on October 1st is called the harvest moon. The harvest moon is the name for the full moon that occurs closest to the September equinox, one of 2 days per year when day and night are of equal length. Most years the harvest moon falls in September, but every few years it shifts over to October. The name traces back to both Native American and European traditions, related, not surprisingly, to harvest time. At the end of October, on the 31st, we'll enjoy a second full moon. When there are 2 full moons in a month, the second is often called a blue moon. There's another more traditional definition of a blue moon, but this is the most well-known. Note that this is the only 2 full moon month in 2020. October is a great time for viewing Mars, as the planet is visible all night right now and reaches its highest point in the sky around midnight. This period of excellent visibility coincides with the event known as opposition, which occurs about every 2 years when Mars is directly on the opposite side of Earth from the Sun. This is also around the time when Mars and Earth come closest together in their orbits, meaning the red planet is at its brightest in the sky, so don't miss it. Spacecraft from several nations are currently on the way to Mars, including NASA's Mars 2020 mission, which is scheduled to land there in February. Finally this month, it's a great time to try and spot the galaxy of Andromeda. Andromeda is also known as M31. It's a spiral galaxy similar in appearance to our own Milky Way, but slightly larger. Both contain hundreds of billions of stars and, we think, trillions of planets. Now, we can't see the overall shape of the Milky Way because we're inside it, so Andromeda gives us a sense of what our galaxy would look like if you could see it from afar. Andromeda is faint and best viewed with a telescope, but you can observe it with binoculars or even a cell phone with a good camera on it, even from light-polluted areas. And under very dark skies, it's just barely a naked eye object. So although it might be a little challenging, it's worth it to see an entire galaxy with your own eyes. To find the Andromeda Galaxy, look to the northeast in the evening sky once it's truly dark. Find the sideways W that represents the throne of Queen Cassiopeia. To the right of Cassiopeia lies the constellation Andromeda, which includes this string of bright stars. Moving upward, hang a left at the second of these bright stars, and as you scan back over toward Cassiopeia, you'll notice a faint, fuzzy patch of light. That fuzzy patch is the Andromeda Galaxy, located 2 million light-years away. If you manage it, congratulations, you've just gone intergalactic. Here are the phases of the moon for October. You can catch up on all of NASA's missions to explore the solar system and beyond at nasa.gov. I'm Preston Dykes from NASA's Jet Propulsion Laboratory, and that's what's up for this month.
Hi, everyone. Thanks so much for joining today. My name is Brandon Rodriguez, and I work at NASA's Jet Propulsion Laboratory in the Education Department here in Pasadena, California. Very excited to have you guys join us today. This is your first time. I'll kind of give a run through about what you can expect if you've been here before. Thank you so much for coming back. I'm really excited about today's topic. We've spent so long now talking about Mars throughout the summer as we prepared for the launch of Perseverance. And you'll notice last month we kind of made our first step talking about the Deep Space Network and this kind of transition to how it is that we manage all of our missions, not just going to Mars, but how do we communicate across the solar system. With today's talk, we're actually going to expand even beyond that. And that's what I'm really excited about. I'll tell you that this topic is of personal interest to me, as this Saturday we have a follow-up session just for educators. So if you're a teacher, there are a few slots left for our workshop this weekend, looking at student and teacher programs in astronomy. So we'll actually have several of my student interns presenting on their research in astronomy and looking at young stellar objects. So to that end, this is a really a double interest, not just as a general topic, but for my own personal research to be able to understand better how it is that we use the entire electromagnetic spectrum to study space. So beyond just visible light, how are we using wavelengths such as in the infrared to study well outside of our solar system to stars and nebulas and galaxies far away? So we have a great guest. I'm going to turn it over in just a second to Jose. But before I do, I'll tell you a little bit about the format for today. We'll have an awesome presentation from him. We'll do a little Q&A. If you register online on our website at the JPL Education site, you'll be able to submit questions to us, which we'll answer here with Jose. And if not, feel free to just continue to listen in. And after that, after that Q&A section, we'll do a little recap of other resources from the education department for you, either as a student, a teacher, a parent, or maybe just someone who's generally interested in what NASA is up to. So with that, let me not delay and turn it over to Jose, who's going to tell us about infrared astronomy and a really exciting new mission.
Thank you so much, everyone, for joining us today. Thank you, Brandon, for the introduction. My name is Jose Siles, and I'm the manager and technical lead of a new NASA astrophysics balloon mission called ASTROS here at NASA Jet Propulsion Laboratory. We're planning to launch from Antarctica this mission ASTROS in 2023, but that's a few years ahead of us right now. I wouldn't call this a clash, actually, but rather an exploration journey or even an adventure, because it's what science is all about, right? In this case, this is an amazing journey, or pretends to be an amazing journey, to fly a giant far-infrared telescope from the most remote place on Earth into the stratosphere to study the stars. And in fact, what you see here in the first slide, if you're seeing it right now, this is a photo that I took of our team on Antarctica back in 2006. So when we were there, it was actually 24 hours of light every day. It was daylight all the time. But a few months before we got to Antarctica, an NSF photographer took this amazing photo from the US McMurdo station. I hope that you can see it. It's beautiful. I mean, every time I see it, I'm impressed about it. I wish I could have seen this in person when I got there. Unfortunately, when we got there, it was already daylight. But anyway, I'm sure that everyone will recognize what it is, right? Of course, this is our galaxy, it's the Milky Way that you can see there. But have you ever taken a second to really understand this view? Because the Milky Way spans 100,000 light years across, which means that if we are on one side of the galaxy, we'll have to wait 100 years to receive emissions from a star that is on the other side of the galaxy. So when we look at the sky, we actually are looking into the past. That's what we see. So somewhat, when we design our radio telescope, we are designing a time machine because we're looking into the stars. Another important thing here is that just in our galaxy, there are between 200 and 400 billion stars. Can you imagine at all how many galaxies are in the universe? Because I certainly cannot. But if we could, and we multiply the number of how many stars are, for example, in our galaxy, the the total number will literally blow our minds. So you will believe me then if I tell you that with so many stars in the universe, it's obvious that they have to play a key role in the evolution of galaxies, like our galaxy that you see here now. So basically, if the stars play a major role in the evolution of galaxies, they also play a major role in the evolution of the universe. However, believe it or not, galactic evolution is still one of the biggest mysteries in astrophysics. And we still need to do more missions to understand what's going on. I like always to say that galaxies are actually living entities. So we have these gas and dust. So all these galaxies are filled with this gas and dust, what we call molecular clouds. And due to gravitational effects, they collapse to form stars. And when that process happens, there are molecular emissions in the far infrared that tell us what is going on in these processes. For example, you can see in here, we have ionized carbon, ionized nitrogen, and atomic oxygen that are being emitted as the star forms. And then eventually planets form, and after millions of years, the star dies, for example, at these huge explosions that we call supernovas. And then all that material is ejected back to the interstellar medium, and the cycle happens over and over and over. So at every step of this cycle, actually, there are emissions in the far infrared that tell us what's going on in this process of star formation. So and remember that every atom of our bodies was produced in one of these cycles, in one of these stars. So don't forget then that any scientific mission starts with a question. And coming back again to the idea of that every atom in our body was forming a star, the question we're trying to solve or to find answers to is indeed where we're coming from and if there could be life elsewhere in the universe. So this is again the universe as we see it today with our bare eyes. It's an optical image that any one of us could take just integrating with a normal camera for a long time. Again, the Milky Way in the center. And now you guys will think, well, that's a pretty quiet and relaxing image of the universe, right? It doesn't seem that a lot is going on after you just told us about the gas collapsing and the star formings and supernovas and so on. And yeah, that's right. You're right. This is a very quiet image. But if we go to the universe in the far infrared, what we cannot basically see with our eyes, this is infrared wavelengths, so our eyes cannot capture them. Now you see all the gas and dust surrounding the stars, right? So it's not quiet anymore. So in all these gas that you see in this image now, they're star-forming regions. They're star-forming. So to understand all what's going on here, we need to build this far-infrared radio telescope able to capture this gas, but not only in the three-dimensional space, but also in dynamics. So we need a 3D map of how this gas moves so we can really understand the processes. Because to explain a little bit better how it is, every molecule of the gas, so we're mentioning carbon, ionized carbon, and nitrogen, and so on, it emits at a certain frequency. So we can tune our receiver at each of these frequencies, and we assign a color is when we get maps at wavelengths that we cannot see with our eyes, like the one that you see here in the infrared. Let's zoom actually into bottom right corner of that image. And that's a nebula there that I'm sure that every one of you guys can recognize in the sky, called Orion. And this is a spectral image taken with the Herschel Space Observatory in the far infrared. And all these emissions or all these lines that you see there are enabling molecules, life-enabling molecules, which means that at a certain point, it could be part of a life form. In fact, 50% of the luminosity emitted since the Big Bang is emitted in this frequency range in the far infrared that, as I said, we can see with our bare eye. So that's why it's so important to study the universe in these frequency ranges. So once again, we want to understand where we're coming from, and that's why we want to receive all these emissions. But the far infrared has a problem, and the problem is that we cannot see these emissions, or all these emissions are mostly blocked by the atmosphere. Not only in the far infrared, but also in the ultraviolet and the X-rays. But if we just focus right now in the far infrared, the water vapor in the atmosphere block this signal, and that means that we cannot put a ground telescope to observe them. We have to go to the space or very close to the space, like, for example, a balloon. Let's think about this as if you have a cell phone, able to receive signals from the stars. And let's try to go to the Atacama Desert in Chile, for example, at 4 kilometers altitude, where ALMA is. I'm sure that everybody had heard about ALMA. And let's see if we have coverage. So the answer is no. well, you can still receive some signal from a star formation in very far away galaxies because they move very fast with respect to us, and the frequency change enough. So now the frequency is much lower, and we can still see them with ALMA. But if we're really focusing on galaxies that are nearby, or star forming regions in our galaxy, we definitely cannot see them from the ground. Okay, so we can say, let's take an airplane. Let's put the sample of the NASA SOFIA observatory. Okay, you can see here that things get better. Your now stellar cell phone gets much better in terms of coverage. But there are still a lot of dead zones in critical points or critical emissions where we want to see what's going on. All right, let's go a little bit higher. And now we have a balloon flying at 130,000 feet into the stratosphere, pretty much 4 times the altitude of a commercial airplane. And now we are over 99% of the atmosphere, above the atmosphere, and our coverage, of course, becomes pretty good. You can see that now our stellar cell phone has close to 100% coverage, and we can see all the signals where the coverage was 0. Now the transmissivity is much better. So that's one of the reasons, and one of the most important reasons for doing far infrared missions with balloons. But it's not the only one. Another important one is, of course, cost. So we have ground telescopes like ALMA. We have said already that for this specific case, we cannot use it, but we could. We're talking about $1,000 million. We can go to an airplane, as I said before, like SOFIA, and we're talking about close to 100 million per year in operations. Now, of course, we can go to space. It's another $1,000 million. A space mission will give you better conditions and a lot of observing time. But because of the cost, the technology has to be very mature, has to be very well proven. And then it takes a lot of years to make it happen, since you have the idea until you fly. But with a balloon, we can do science missions with around $10 million. And because of the lower cost, we can take higher risks and accelerate the infusion of the new technologies to test them in flight and pave the way to future space mission. But in addition to that, we can train the new generations of scientists and engineers that at some point will become leaders on space missions. So it's a great training camp for these new generations. And also, of course, we can land the radio telescope back on Earth after the flight and update it and fly it again. And the technology that we use in balloons is not only, for example, we're talking here about astrophysics, but the same technology, talking, for example, of this mission that we flew in 2016, called STO2, or the technology that we're going to fly on Astros in 2023. So the same technology can be used for detecting, for example, water in ocean walls like Europa, the Moon and Jupiter, or in comets, or to monitor our planet's health, for example, the ozone layer, or even to look at humidity and rain forming inside the clouds to improve weather predictions, basically to improve our life on Earth. All right, so we're talking about balloons, and I'm sure that now maybe you are thinking, wow, using balloon is a great idea that you guys just had. But some of you probably instead are thinking, what are you talking about? Balloon is a rudimentary flight technology and has been around for many years. And you're correct. Balloons have been around for many years. In fact, NASA's first balloon mission was in the 60s, and it was called ECHO. It was a passive reflector for communications, inflated in space at 1,500 kilometers. So it was used for communication, but did some measurements as well of the atmosphere. But do you really think it was the first scientific balloon mission ever flown? Think about it for a minute. And the answer is no. So actually, in 1912, Victor Hess took a hot air balloon and went all the way up to 5 kilometers, measuring the radiation as a function of altitude. And in 1936, he received the Nobel Prize for discovering the cosmic rays with an experiment from a scientific balloon. So more than 100 years ago, which to me is really impressive. And since then, more than 1,000 missions and still counting. So yeah, indeed, balloons are not something new. So we have been doing it for more than 100 years. All right, so I'm sure that at this point, and after all what I've been talking about balloons and astronomy, you already know that radio telescope is not more than a radio. But instead of tuning to your favorite music station, we just tune to our favorite star emission, to these ionized carbon or ionized nitrogen or atomic oxygen emissions. But there's a problem or a caveat here, and it's the frequency. So a regular radio, for those that remembers the old radios working at around 100 megahertz, a radio telescope like the one that we are building is working at 20,000 times a larger frequency, which means the circuits, the receivers that we need to capture these signals are much, much smaller. In fact, the receivers we need to fabricate to detect the emissions from the stars fit inside a human hair. So that adds a lot of complexity, of course, to building this radio telescope. Okay, so then we take these circuits, we assemble into housing blocks, and then we put them into a cryostat filled with helium because we need superconductors to be able to detect these signals. They are very faint signals, so we need a very low noise and very good sensitivity. So we need to operate at 4 Kelvin, close to the absolute zero. So then we attach this cryostat to a big antenna. It was 0.8 meters for STO2. It will be larger in Astros. We threw in there some motors and reaction wheels to control the pointing, because of course now we are hanging on a balloon, surfing the airs in the stratosphere. So we're basically getting a ride, and we need to constantly point the radio telescope to our target. We need car batteries and solar panels for power the telescope, and of course antennas to receive the data and for communications. And then after all that is put together, we have our telescope that you can see in the slides here. Altogether, around 20,000 parts. I haven't counted them for sure, but it's an estimation. From very, very small parts to large parts that you put together in 4 years and test it here first in the US to make sure it works. And when everything is working, surprise, we need to take it apart, put it in boxes, ship it to Antarctica, and do it again. And do it again in 3 weeks. So it's like, are you kidding me? You have gone to this point where everything is working and you're going to take it apart? So yeah, that's what we're doing. Exactly what we're doing. And why Antarctica? Well, the first thing is safety. If something goes wrong, there's no risk for people or infrastructures. The worst thing that can happen is maybe a big hole on the ice. You have to basically do a crash land, but not a big deal, right? But the important thing is that we want to take advantage of what we call the Antarctic vortex, because we have this circular wind pattern that forms in the summer in Antarctica, and that pattern makes the balloon, when we launch, circling around the continent for a few weeks, and then since it doesn't goes outside the continent, we can land and fly again next time. So that's another advantage of doing it in Antarctica. So Antarctica, here we go. The team gathers in LA after taking everything apart and put it in boxes, as I've said before. We leave from LA a few hours in Sydney to transfer to New Zealand and give us some time to visit the Opera House, of course, which is beautiful. Then to Christchurch, New Zealand, for survival training and getting the cold weather clothes and all the orientation and prepare to go to Antarctica. And from there, we take a US Air Force plane to McMurdo. So pretty much this is the process. We start with my luggage that you see here, and you will be thinking like, why is so interesting to see your luggage? Well, my luggage, in fact, is not interesting, but there's some black boxes that you see there, which are actually parts of the telescope, because these parts, some of them are so sensitive, so delicate, that we need to carry them with us. We cannot just put it in a ship for 6 months. We need to make sure that they are transported correctly. So it's really funny to go to the bottom of the wall with a box full of things that you can imagine how it looks in an X-ray in the airport. So it's it's an interesting process. Then you get there, you see there, or you can see there a photo of me with all the cold weather clothes. It's not that I wanted to just to put the photo there for social media. It's just that they make you wear these clothes when you get into the airplane. And the reason is that if something happens, I mean, if there's an emergency and you have to land in the middle of the nowhere in Antarctica, I guess that maybe you can survive a few hours. You have a warm clothes. Probably not much more than that. And then, yes, we get into the airplane and we fly as cargo. But look how much leg room you have. It's much, much better than a commercial flight. So we get to Antarctica, and the runway is just ice. It's a very nice runway, which is just the frozen sea, pretty much. So it's a very interesting experience. You have McMurdo Station here that looks like, of course, all scientific base. You can see the main galley in blue somewhere there. You can see the dorms and maintenance buildings and so on, everything you need to survive for the 800 people that are here in the summer. During the winter, when it's nighttime all the time, we're talking about just 40 or 50 people. We have a gallery, we have a clinic, a small clinic, a fire station. We have a beach, a frozen beach. And you have something very interesting, which is this hat there that Sir Robert Falcon Scott built in 1912 when he was doing his exploration to the South Pole. So it really feels when you see this kind of thing like you are one of these explorers from the early 20th century. By the way, 1912 was the same year that Victor Hess did his balloon experiments, which is a nice coincidence. And a lot of ice. It's Antarctica, so you have a lot of beautiful ice, like you can see here. We were not building the telescope in McMurdo. We were in a NASA facility called Long Duration Balloon Facility. That's where we have to rebuild the telescope in 3 weeks. And you can see here a nice day. And when you have a storm, basically everything gets wiped out in minutes. So you go from having an amazing view to not seeing anything. And that's why you really need a survival training, because if that happens, you better just put your tent there and don't move, because you have crevasses on the ice and all that. So you don't want to be wandering around without really seeing where you're putting your feet in. So that's why it's important as well, all this training. Inside the hangar, it's quite comfortable. We have heaters, of course. But it's obviously not easy to bring things to Antarctica. It's not obviously easy to rebuild a telescope that you have built in 4 years in 3 weeks. And you need to make sure that you brought everything with you that you need and everything you might need to fix anything that might go wrong. Because if not, it's like Apollo 13, the movie, if you guys remember, when they have to build these CO2 filter adapters with whatever they had in the spacecraft. So Antarctica is the same. If you miss something, you have to do it yourself. So believe me, it happens. So where are the stars in Antarctica? Right? We're building this telescope, but now we have to look at the stars to try it. But it's 24 hours daylight. And I have told you before that the atmosphere blocks all these infrared signals. Okay, so we don't have the stars, or we cannot receive from the ground the emissions from the star. Well, let's create our own star. Easy, right? So we put a transmitter simulating a star that you can see in front of the telescope. We send the signal to a reflector antenna, and we point the telescope to this reflector antenna that now is a fake star. It's an artificial star, but allow us to basically make sure that the telescope is pointing to the correct position and that we receive the signal of the stars. And there's another advantage of creating your own star, is that if you want to make sure that you are pointing to the right star, well, it's easy. You go there and switch off the star. So what you do in this case, you go there and you put your hand with an absorber in front of it, and if the signal disappears from the telescope, great, you were pointed to the right place, and then you're ready to fly. So as I said, 4 years, 20,000 pieces back together with all the cables and receivers and solar panels and the telescope and the parachute and the software, cables, everything working in 4 weeks to get to the point where we are ready to launch. In this case, that's from STO2, beginning of December 2016. And so our time machine is ready here on the right. The flight configuration on the left, you see the 400 feet balloon, 400 feet diameter, is as large as a football stadium with 40 million cubic feet of helium. It doesn't look fully inflated because of the different pressure between the ground and the stratosphere. It launches like that, but when it arrives to float altitude, it's just a perfect sphere, and it is at that point fully inflated. So it's connected to the payload that you see there, very tiny, hanging from the launch track. It's connected with a 900 feet cable. So let's see now a video how we got to this point and how we launch. So, well, I cannot see the video myself in the image, but what is going to happen basically, you start with inside the hangar. You're going to mount the payload into the telescope. Then the payload and the telescope is connected to the gondola. When that happens, all the solar panels are connected basically around the telescope. You can see all that process. Once you have everything mounted, you're going to basically try to wait until all the electronics work, and you're going to go outside and do all the communication tests, make sure that you can monitor the telescope, and you can basically make sure that you can command it, that you receive the data and everything. When that's ready, you go back inside, you wait until you have a launch opportunity. And when you have a launch opportunity, you have to go outside, do all these tests again, and basically when the air is calm, you wait to go to the launch pad and you release the balloon. So the balloon gets released. So basically you see it is not fully inflated, as you saw in the picture and you'll see in the video. You release the balloon climbs slowly. It basically gets aligned on top of the launch vehicle. And when that happens, you backtrack the launch vehicle, you release the balloon, and then basically the radio telescope start climbing. And you have to basically back off in order to avoid the radio telescope to hit the hanging structure where the telescope is hanging from. Then it starts climbing to the stratosphere. It's a 2 hours climb. At the beginning, you'll see that it's spinning a little bit. It's not a big deal. When you get to float altitude, you have reaction wheels basically to point at that point the telescope and avoid the spinning. You also have an elevation drive to do the pointing, so you're sure you're pointed at any specific target at any given time. You'll see also in the video the view from inside. So it's very impressive when it gets released, how close you get from the launching vehicle. As you climb, you can see also the Mount Erebus, which is a supervolcano that is there in Antarctica. So it climbs. We fly for 21 days. And after 21 days, what happened is, for terminating the mission, we tear the balloon apart. And for that, we just release a mechanism. You'll see the balloon basically breaking apart. And very, very small on the bottom, you see the parachute deploy, the payload and the parachute deploying to basically land back on ice. There's an image. You can see how tiny the payload is compared to the radio telescope compared to the huge 400 feet balloon. And you can also see the view from the altitude, how the Earth looks like from that altitude. And at the end, you land back on ice, and you basically can recover and eventually fly again. So I don't know if the video is still playing. Maybe Brandon, you can give me a sign when it's over.
That's good.
Okay, so if you have ever seen the guys at JPL Missions Control during a Mars landing, so see how fancy it is. Well, for balloons, it's as exciting. You have seen the video and all this process of the launch and operation, so you can imagine how exciting it is. But it's not quite fancy in Antarctica. It's like your garage. It's very cool because you're in Antarctica, definitely very cold, but not as fancy as JPL, indeed. We're working inside the hangar. We haven't slept for many hours at that point, but pretty much if you compare the two photos are very similar one to each other. Less people in Antarctica than in here at JPL for a Mars landing, but as I said, the same excitement. We flew for 21 days. Here is the path. And we look for a sample into one of the most active star-forming regions in our galaxy, the Carina Nebula, that you can see here. And in the right, this is raw data. This is the data as we receive it with the radio telescope. In the lower right, you can start seeing peaks, and those peaks are actually carbon emissions. Those peaks give you the velocity of the gas and also the abundance, and you can turn that into an image. And that image that you see in red in the center of the screen shows actually that there are stars forming in that region in the Carina Nebula. And this is actually when we can say that it's mission accomplished. It was a long journey to here, but the mission was a success. But the only way to make it happen is teamwork. This is true for any scientific mission. Teamwork is the key, but even more for a balloon when you spend 24 hours a day for 3-4 months there on the ice, 4 years before, but especially when you go to Antarctica, it's 24 hours working together, living with these folks, and you really need to trust each other and get along to make it work. And that really makes these scientific balloon missions from Antarctica so special. Just sharing these moments with the team there is just extremely rewarding. And then, of course, as I said, we can fly again. The answer is definitely yes. Let's take a rest first. And you will see here some penguins at the end of the season taking their rest. The team did the same. And now, a few years later, we did take our rest. And a few months ago, we started working in a new mission that is going to fly in 2023. And I already mentioned the name, which is Astros. And what you see here is a different graphics, but it's the same star forming cycle that I explained before. And what we are going to focus on Astros is how supernovas, this huge explosion, modify the gas and then regulate the star formation. Because otherwise, all the gas will have collapsed into a star really fast in the early universe, but we know that that doesn't happen, that there are a lot of star formation going on. And that's what we really want to study with Astros. But what we're going to do is to fly a telescope which is 3 times larger in diameter, 9 times larger in collective area, because we want to see outside of our galaxy and inside of our galaxy and compare those galaxies or those star-forming regions in different states of evolution. We're going to fly newest technologies that we have now. For example, we are not going to use helium liquid in this case. We're going to use an electrical cryocooler, so that means that we can fly much longer. And also we can reduce weight, and that allow us to increase the size of the telescope, which in this case, as I said, is 9 times larger in area. But again, that's 2023. We're very excited. We'll be in Antarctica in a few years to launch these new exciting missions. But I'm going to finish, while we will until 2023, with this paragraph that I wrote in 2016 after the STO2 flight, and says the following. Today, we got the first detection of carbon emitted by nearby Eta Carina 7,500 years ago. That's the time the signal takes to get to Earth from the Carina constellation. Carbon is basic to life, and these carbon emissions we are seeing today might turn into life in several million years from now. So likewise, ourselves, our carbon was probably part of a distant star-forming region millions of years ago. So today, as we look at the stars from the most remote part of our planet, using a large telescope on a giant balloon, we dig into our past to try to understand our future. Thank you very much, and happy to take any questions now.
Really, really awesome. Thank you so much for that. I learned a ton. This is a really interesting kind of look at this new technology that's old technology, right? But doesn't get hyped the same way that a lot of these missions do, right? I mean, like you said, we kind of hear about the big missions to Mars and so forth, and the big crowded rooms, and we see how many hundreds of people work on this. But this, those are expensive and time consuming, and to hear about these kind of recyclable and kind of quick turnover types of missions, that's pretty amazing. We got a ton of questions that I'm hoping to ask you. I'll start with a few technical ones while it's fresh in our heads. You kind of mentioned close to the end that you're switching away from the liquid helium, and that's going to allow you to be able to kind of stay afloat longer. Is that the limiting factor, or did you get the information you needed, or like how long would you want to stay up if you could, to have a complete mission?
Well, the Astros mission, when we fly, our baseline science is 21 days. But that's mostly defined because, the Antarctic vortex sets for 3-4 weeks, right? So when the winds are gone, you run the risk of drifting off continent and losing the payload, right? Because we'll have to recover in the water, and that's not possible. So you want to finish the mission before that happens. But for a future space mission, you could fly longer. You could try to basically fly a superpressure balloon and recover, for example, in Chile and other places, or maybe the wind pattern lasts for more weeks. When you have helium on board, you are limited by the amount of helium that you have on board. So basically, it could be like 2 weeks, 3 weeks, something like that. So once you run out of helium, your superconducting receivers don't work. So it doesn't matter if you can keep flying. The balloon will keep flying, of course, as much as you want until you terminate it. There is no, in principle, no limitation on that other than you wanted to recover on the ice. But if you run out of helium, you just cannot keep doing science. However, if you have electrical cryocooler, there's no limit to that. So you could keep flying as long as your winds are settled, and you can still take advantage of them. But also, we said in the beginning that we want to do this to infuse the technology in future space missions. So, for example, there was a mission, a similar kind of technology called Herschel that I talk about a little bit. And Herschel lasted 3 years on space because it had 3 years of helium. So now we flew a new mission similar to that one, but with a cryocooler, then we won't be limited to 3 years. So we prove it in a balloon in a similar kind of mission, then you can you are ready to put it into a space mission. And
Interesting.
That's one of the goals.
That was kind of my follow-up question, which is, what is the advantage of this? Why not fly a ton of balloons instead of a Herschel and a Spitzer? So you're saying that the technology you're testing now will feed into that. Are there any other technical advantages of why we would want to, be in space instead of just orbiting with a balloon?
Well, of course, the atmosphere is perfect in space, right? In balloons, you're over 99%, but you still have some impact of the atmosphere. Also in space, you're collecting data, for years constantly, pretty much. In a balloon, you fly for, let's say, 4 weeks, and then you have to land back, and then you have to wait another year until you can launch again. So you basically are taking science in periods of 1 month at a time. So it's much cheaper, but you have to do it more often. So it depends on your science. It might be just easier and enough to do it with balloons. Maybe you have to take data for so long and you have already your technology ready, and you want to go to space. Or it's somehow in between, right? That you can do part of it still on a balloon. You take the opportunity to fly very fast new technologies that otherwise will take like maybe 10 years to get to the point where you are ready to go to space, qualify somehow to go to space, and then once you have demonstrated in a balloon, just go to the next step and prepare your flight mission. But you know that at that point you have accelerated the maturation of the technology.
Yeah, very cool. Another question was actually about that turnaround. So now that you've been up and you've got your data and you have this parachute where you're hopefully landing safely so you can turn around the payload, what is the velocity when this thing hits the ground? What's the risk, and what does repair and testing and recycle look like?
It's a very mild landing. I don't remember exactly the number, but it's just a very few meters per second. It's a very smooth landing if everything goes well. You have some some pads that somehow helps to make the landing a little bit softer. Actually, you have seen in one of the slides how the payload looks like right after recovery. Of course, the solar panels are damaged after landing, but those are very cheap and you don't care about that. But the rest of the structure and the telescope is all working. Actually, we switched everything on in the ground after recovery and everything was working, which was pretty impressive. We could basically fly again in the same configuration. Now, of course, you always want more, right? And that's why the balloons are great. You want, at that point, 4 years later, you have newest technology, and that's what we want to do in Astros. Now we, based on the same kind of science case or trying to go a little bit beyond, but also similar technology, but now we want to have more receivers. So it's like a camera. You want more pixels. You always want more pixels to be able to get better images. You want a larger antenna because you want to go now to extragalactic sources. With the flight that we did in STO2, the telescope was so small, so we couldn't really look outside of our galaxy. So you want to expand it, make it larger, with things that you have already proven, and fly again. So the new gondola is actually probably 3 times larger than that one, because the telescope is 3 times larger in diameter. So if that looks big, the new one is going to be much more impressive.
Yeah, there's never good news, right? Because it's always, now we have more questions. Now
exactly. I always say that no matter what you give to the astronomers, that they always want more, and that's how it's supposed to be, because that means progress, right? We try to aim for very difficult or impossible things, right, and make it happen. Like they're mighty things, right, as we say at JPL.
From the balloon side, has there been any evolution in that technology? What is the balloon made out of? Is there progress there, or is that kind of understood?
The balloons, the NASA balloon program office keep evolving the balloons. For example, this balloon we used was a zero pressure balloon. You can fly as I said, a few weeks. They are working now in a super pressure balloon that can fly much longer and go through day-night cycles. The material of the balloon is no different to the material that you will have in a supermarket bag, in a typical supermarket bag. It's a 2 millimeter thick plastic, polyethylene, and so yeah, it's not very special if you think about it. It's as well very well understood material and process.
Yeah, the chemist in me appreciates like that pressure is doing the work, right? As you mentioned, it doesn't even look full at where we are when the pressure is kind of collapsing the balloon, but as it reaches altitude, that change in pressure allows it to open up.
Yeah, we go in the ground. We have one atmosphere, and we went to 130,000 feet. The pressure drops between 0.3 millibar and 3 millibar, and that what makes basically the balloon to span and fully inflate. But you of course have to calculate very precisely the amount of helium you put in the ground to have the correct inflation at altitude.
Yeah, so for kids at home wondering why Boyle's law and Charles' law, why these are important, this is
exactly all the maths and get it right, because you cannot go up there and try to inflate it on the fly, right? So
one more technical question for you: why infrared in the first place? Why are we looking there and not like Herschel? Was looking at other wavelengths. So what is it about infrared that's so interesting?
Well, Herschel had many instruments. One was HiFi, that was exactly the same, similar frequencies, the far infrared of some millimeter waves, as we call it as well. I've gone through that in the presentation very briefly. So part of the reason is that 50% of the luminosity since the Big Bang and 98% of the photons basically were emitted in this frequency range. And that's something that COVI, a previous NASA mission, discovered. So talking now about the star formation, pretty much all the key tracers that allow us to understand every single step of the star formation process are in the far infrared. It just happened to be there, which is not surprising because of what I just said, that many of the missions since the Big Bang are in this frequency range. So that's why, for example, just to mention a specific case, ionized carbon and ionized carbon and atomic oxygen are the major coolants of the star forming regions, which means that when you have all this material collapsing and the temperature increasing, there has to be something that cools down the molecular cloud so the star keeps forming. So basically that collapse doesn't get interrupted. So that happens because of emissions of ionized carbon and atomic oxygen, which are in this far infrared. So if you are able to detect those signals, you can infer that this star forming process going on there.
Awesome. If we could talk a little bit about you and your journey to JPL, several people are wanting to know. I mean, how did you kind of get into this path? I mean, I'm sure you didn't take some high school science classes saying, "Oh, I'm going to Antarctica to send balloons," right? It's pretty niche mission. So how did you get to where you are now?
So that's an interesting question, actually, because I mentioned Apollo 13 during the presentation. Apollo 13 is very important for me because I watched I didn't watch the launch, of course. I mean, I was not born back then, but I watched the movie when I was 15 years old. And I remember that scene where they were trying to fix that problem and bring back the astronauts alive, back to Earth. And I was just, I fell in love with NASA. I was from a small town in Spain, in Andalusia, a very small town. I was a little kid. I saw these NASA engineers working together and doing impossible things, and I said, wow, that would be a dream to work in a place like that. But when you are not American, and I couldn't even speak English back then, it's not that my English now is very good either, but it's much better than it used to be back then. So I got impressed, but I thought it was impossible, right? How you get to here. So I just wanted to play with technology. So I studied electrical engineering after high school. And then I got just by chance into a project for the European Space Agency through the university to design or to do modeling for this kind of receivers. And at some point I started through conferences meeting people also from JPL, and I ended up doing my PhD between Madrid, Spain, and in Paris, in the Observatory of Paris, working on this kind of technology. And eventually, I got a Fulbright scholarship to come here at JPL as a postdoc. And again, that was like a dream come true, right? And you get here and say, I hope that at least I can be here for a few months. Let's see if I'm good enough. And but as you know, when you get into JPL, everything's so exciting and so many projects, and it's been 10 years since that first day. And it's an amazing place to work, and for me, it's like fulfilling a dream. I just love what I do, and and if even you get to go to Antarctica and fly things from there, it's just impressive. It's something that I couldn't have thought about when I was 15 years old, and I thought it was an impossible dream to work for NASA.
Yeah, it's such a it comes up so many times when we do sessions like this for our international audience is always wondering how can I make this happen, and it really does seem like those not just agency but university partnerships kind of create some inroads. So it's really kind of motivating to hear that.
Yeah, and I think that's the key point. I think you never should say to yourself that something is impossible. I think you just need to do the best, just to enjoy it and enjoy studying and enjoy your research, and eventually things happen. And that's the key part of it. I was a normal guy, like every one of us, every one of the kids that probably are watching us. I just need to do what you like to do, and eventually you get where you want to be. Of course, there's hard work, and sometimes you have to be in the right place in the right moment. But it is not impossible. It's more doable than what we think when we're little kids.
Yeah, most definitely. And as someone, I've only been here now for 5 years. This is not my first job out of school, and that's totally fine. I wish our students understood that you don't always hit the home run. You don't always get the dream job on the first stop. I was fortunate enough to have a great job coming up, but obviously when NASA called, it was that time. So you work hard and you kind of chip away at it sometimes, but you do get to these awesome places and do research as incredible as this.
And there's another important point, which is not being afraid of making mistakes. It's difficult to send something to Mars, but it's also super difficult to send something from Antarctica to the stratosphere in that tight schedule. And you can basically put that sample to any project at JPL or at NASA. You just need to trust yourself, trust the people you work with, and not be afraid of making mistakes, because, you never get it right at the first time. So you just keep going and keep trying, and you learn from your mistakes, and you get to the point where we can land amazing rovers on Mars, for example. So that's something that is very important, as well as you go through your student life, to realize that you shouldn't be afraid to get it wrong the first time, or the other way around. I think that you learn more from the mistakes than if everything was perfect. So that's another key point for the students, I think.
Yeah, it's such a great message to kind of wrap up on, that in this day and age where students are so afraid of getting the wrong answer and thinking about grades and kind of the next step, college, grad school, etc., that the real world really does appreciate failure and iterative learning and kind of growth in that way that maybe we don't see in the way that school is kind of typically run.
Mm-hmm.
Well, thank you so much for joining us. I really, really appreciate it. It's just awesome to kind of get this insight as to crazy cool missions to look forward to in IR astronomy. If there's a seat in that cargo plane next time, please take me along. But yeah, thank you so much for your time today. We really appreciate it, and I'm sure everyone really enjoyed. Thanks so much.
Yeah, thank you for having me. And definitely, let's hope that everything goes well. And 2023, maybe we can do another one, but this time from Antarctica, and we can talk to everyone and show things real time as they are happening there, doing this an event like this from Antarctica. So thank you again, and thank you for everyone that is listening or watching us. Hope everyone enjoyed, and yeah, thank you so much for the opportunity.
Great. So with that being said, I'm going to transition to a few slides again on some educational resources and just further reading exploration that you guys can do if you're interested in this topic and you want to learn more. On my first slide here, you'll see just kind of our landing page. This is the JPL Education website. And you'll see up at the top, there's a banner of options here, ranging from intern to share, where you guys can kind of walk through different types of activities and resources based on your interests, whether you're a teacher, whether you're independent learner, or you just want to read a little bit more about what's happening at JPL and NASA overall. On my second slide, you'll see some of these lessons that we have in that teach section. Again, if you're an educator, whether in the classroom or at home, we're really trying to explore this further. Why is color and wavelength important for understanding our solar system? And in fact, you'll see a stack of images on the top taken at different frequencies, really giving us very, very different information. And, so we heard a little bit about why infrared is interesting, but again, beyond that, different wavelengths really tell us different things about what we're looking at. And you can model this in the classroom or at home using different things like filters, which we'll hear a lot more about on this coming Saturday, as we kind of model actually some of these activities and look at how light and filters interact with different objects. On the third slide, you'll see another example lesson. This is kind of our take on the old cereal box type of spectrometer. And this is really interesting when you look out into space, where again, maybe the visible light, like you see in the left-hand picture labeled A, gives you something, but clearly something's different in B, where you start to get a little bit more of the where chemistry and physics come together, much to my delight. And you can see a little bit more about kind of the atomic subtext. What elements are there? Like we heard Jose mention about looking at things like carbon and oxygen. We know that every atom kind of has a very specific spectrum. So matching that light against known spectrometers and filters, we can actually see what elements are being contained in some of these images. On slide 4, you heard us mention last week, if you attended, if you didn't, this is recorded and on the website, talking about not just how color, like and by virtue of wavelength is important, but again, how distance is important too. How does light move across space? How does it expand and dim? And how is it that we're able to communicate with spacecraft as we send them further and further into the solar system and beyond? So we have a lot of demos and activities around that as well. So on slide 5, you can, again, this is kind of our news section written for the general audience. You can read more about all of these topics. There's drop-down menus to kind of walk you through different categories of things, whether your interest is more on internships, education, or just, again, kind of current events from JPL. On slide 6, you'll see a closer look at our teach section built for educators, which, again, really, really easy to navigate website, has these drop-down menus so that you can target what grade you're interested in. You can search for individual topics and themes so that you can really get to where you're going. And this, again, is something that we'll highlight in our Saturday session just for educators. The same thing on slide 7, where, again, this is written a little bit more for self-directed learning. So if you're a student or you want to assign a lesson to your class or to your children at home, this is written with the idea that they would run this themselves. They're able to kind of follow step by step and do these little online labs and activities to learn more themselves. On slide 8, you'll see our education resources overall from a web page called Learning Space. And here you'll kind of get a feel for a conglomerate of all of these things put together for students. So all of these activities, we have video tutorials that we filmed, translated into Spanish, and just kind of frequently asked questions for families as well, as we kind of navigate this wild world of distance learning and the schools potentially being closed where you are. And then lastly, I'll tell you guys that if you want to learn more, we have put together a kind of thematic exploration just on this topic on our Teaching Space website, where you'll be able to find all of our activities, images, games, etc., all aligned to this kind of light and astronomy theme. And you'll see that at the Teaching Space website, where you can kind of navigate and learn more. Really, really beautiful images. I highly recommend taking a look. So with that being said, I'll wrap up. I thank you guys so much for joining us. I hope that you're really enjoying these events, this monthly series. I'll remind you guys that these take place monthly. They're recorded and placed on our Teaching Space website. So please tell your friends if they can't make it, they can always rewatch later. And they're always followed a few days later on the weekend for an educator-specific session where we'll just have teachers and really explore some of these lessons and the offering of activities in a hands-on kind of conversational way. So I hope to see you next month. We're going to look at ocean exploration and a little bit of oceanography. And thank you guys so much for joining us today. Have a great day.
Good at the vehicle. Good. 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 Good spark. Light showing green.
So Masson has been a part of the Flight Opportunities Program since its inception. We were one of its first customers.
Copy that in progress.
There's a lot of benefits. One, we get to fly our rocket. We're always testing our own hardware. Two, we get to interface with like-minded individuals who have, at the end of the day, the same goals, which is to go to the moon, go to Mars, go to these other bodies. And so we get to interact with them. We get to understand how they do things. There's a transfer of knowledge both ways. And we build these strategic partnerships that are only going to facilitate these broader and deeper areas of exploration that we ultimately want to do.
Confirming that test site's up, vehicle payload are good, and we're ready to start the checklist.
So Masson is the flight provider of these flights.
Ground crew in position for a quick check.
We fly the vehicle through a trajectory that mimics that target destination, whether it's the moon or Mars, and gives them the fidelity of data that, again, they're not going to get with conventional means, whether it's a balloon, a helicopter, or an airplane.
We go. Masson ops to all, 6-second count to engine start.
So the Safe, Precise Landing Integrated Capabilities Evolution Project, or SPLICE, is developing a family of sensors that are required to land safely and precisely on the moon, Mars, and any other destination. Testing on rockets gets us even closer to that lunar landing-like test, where we can get as close as we can to that actual lunar landing here on Earth, allowing us to have additional confidence that our systems are going to work when we actually go to the moon.
Terrain relative navigation is a form of navigation in which you are able to determine your state of the vehicle relative to the terrain itself. So we're able to identify features pre-launch based upon satellite maps, load them onto the vehicle, and then we fly a camera on board which takes images. We compare those images to the maps that we've loaded with the pre-identified features, and from that we identify the features in the images captured, map them to the satellite maps, and then from that we can tell relative where we are to the terrain, so we can get altitude and whatnot relative to the terrain that we're seeing. So I think it's going to be critical for future flights. Most of the future missions that we're looking at are going to be pretty much autonomous, try to keep as much human interaction to a minimum. So in order to be able to navigate at the moon where we don't have GPS and other very accurate state information, terrain relative navigation is kind of your next best. The vision navigation portion of it is kind of the next best thing that we can go with. So I think it's going to serve a critical part in the upcoming return to the moon.
Also, as we move towards a sustained presence on other bodies like the moon, we'll need these precision landing capabilities in order to deliver cargo nearby where we have our crewed outposts.
ever considered how big breakthroughs in science, engineering, and medicine occur? The popular misconception of how a breakthrough happens is perhaps a eureka moment while working on a project, and in that instant, the next big thing is born. Although that may happen sometimes, the truth is that most big breakthroughs are not eureka moments at all, but actually take years of painstaking work, trial and error, and rigorous testing before the finished product is ever realized. Researchers in the world of engineering and science almost always move in small, incremental steps, slowly building the case for these new revelations until they are sure the research is ready to be shared with the world. Then, and only then, is when we in the general public hear about it. Although it may not be quite analogous, just think about the moon landing as an example of this phenomenon. Most of us are familiar with Neil Armstrong's famous words when he first stepped onto the moon.
That's one small step for man, one giant leap for mankind.
For those watching it, that moment may forever be viewed as perhaps the most tremendous scientific and engineering breakthrough in the history of the world. Clearly, that event was enormously important for many reasons, but that first step on the moon was actually the culmination of millions of smaller incremental steps from tens of thousands of others that allowed it to take place. This basic idea is true for all scientific study. Researchers and engineers generally take an idea and meticulously study it to make sure that all bases are covered before new technology reaches the general public. NASA's Environmentally Responsible Aviation Project team members are following that same philosophy as well. This team has been working for years to find ways to reduce aircraft drag, aircraft weight, fuel consumption, engine emissions, and aircraft noise. In order to achieve these lofty goals, the team did, in fact, take incremental steps to make sure each project was viable. Now, toward the end of the ERA project, the team is ready to take the lessons learned from the smaller tests and begin putting all the pieces together, preparing to show the world the next big thing in aeronautics. NASA X has been at the forefront of the ERA program since its inception. This 6-year endeavor has progressed from innovative ideas to multiple designs, wind tunnel tests, and actual flight hardware. And the aerospace industry has taken notice that these technologies are ready to dramatically improve aircraft efficiency. Part 1 of this episode of NASA X looks back at some of ERA's earlier tests to see how those early successes and failures paved the way to the larger, more advanced tests of today. And we will see what the future holds for many of the ideas and technologies that have been developed by some of NASA's best and brightest engineers and researchers. When the Environmentally Responsible Aviation Project was first implemented, it was clear the stated goals would be hard to reach. The team was tasked to reduce aircraft drag by 8%, reduce aircraft weight by 10%, reduce fuel consumption by 15%, reduce emissions by 75%, and reduce overall aircraft noise by 75%, all by the year 2025. Compounding the difficulty of making such dramatic improvements was the fact that many in the aviation industry believed that the modern tube and wing-shaped aircraft had reached its maximum ceiling on efficiency. When NASA first undertook this challenge, they realized they would have to bring an A-team of NASA engineers from numerous NASA field centers, along with highly skilled teams from industry and academia in an effort to find these new efficiencies.
We've got new airframes, 8 different technologies that we've worked in Phase 2, a myriad of 60-something technologies we worked in Phase 1 and we looked at. And we will be delivering at the end of this year technologies that say we can meet all of those goals. So it is an unmitigated success, and every one of our partners in this is getting something out of it.
Some of the major areas of study for the team included looking at engine redesigns, airframe redesigns, materials testing, and even developing new aircraft that integrate the wings into the aircraft body to increase efficiency. This unique design is called the HWB, or Hybrid Wing Body Aircraft. The HWB began its life as a series of computer models and then was upgraded to sophisticated wind tunnel models. Once the team was satisfied the HWB concept showed significant promise, it was upgraded to a flying scale model aircraft. 122 times the hybrid wing body models flew over the dry lake bed in California, where so many previous X-planes had flown before. And with each flight, the engineering data helped validate this unique type of aircraft design. Researchers feel confident that the strides they have made in this aircraft design will pay huge dividends in the future. Just watching footage of early aircraft shows how far we've come in only 100 years. As an example, most early planes were made out of wood and canvas, but as planes became more powerful and efficient, materials began to change. Today, we're aware that most planes are made out of lightweight aluminum skins, but the industry is moving toward the use of composite materials now as well. In fact, the Boeing 787 was the first all-composite airplane ever produced, and it took its first commercial flight on October 6, 2011. Although this plane is state-of-the-art, NASA's ERA planners believe that they can improve the strength of composites while making them safer as well. The idea they're investigating is called Perseus, or Pultruded Rod-Stitched Efficient Unitized Structure. Early testing began with small pieces called coupons. They were developed to a point where researchers believed they could be tested on a larger scale. NASA's team built larger test sections and eventually brought them to this lab for stress testing. With this test, designed to bring the article to failure mode, the team applied pressure until the piece snapped. The data was used to further validate Perseus, and now the team has decided to build and break a nearly full-scale piece of Perseus material.
NASA and Boeing have been working together for quite a few years developing lightweight structure for commercial transport aircraft. What we're seeing today is the final piece of a project called Damage Arresting Composites, where we're trying to develop a new structural concept that will be applicable to lightweight structures for commercial airplanes. And what you see here is a 30-foot-long test article that we'll be testing at the NASA Langley Research Center by applying the kinds of loading that it would feel if it were in a real airplane.
But with a piece this large, a major hurdle lay in front of them: how to get the piece from California to Virginia for testing. Traditional methods like trucking and train travel would not work due to bridges, overpasses, and some road weight restrictions. The solution was to fly it across country, but no ordinary aircraft would do. Ultimately, the team enlisted the service of NASA Johnson's Super Guppy aircraft for transport across country. This Cold War era aircraft was specially designed with a hinged front-loading system that could just barely accommodate NASA's cargo. It was not lost on team members that this old and slow beast of an aircraft was transporting a test article that will undoubtedly be used in many aircraft of the future. On a cold December night, The aircraft landed in Virginia for an early morning offload. Here is Dr. Faye Collier to explain what is next for this test.
Today we're here at Langley Field unloading the Perseus multi-bay Colts multi-bay box that will be tested in the Colts facility. So we've been working on Perseus for about 10 years now, partnered with the Air Force, partnered with Boeing, R&T, and we started off with small coupon testing to prove out the concept. We built a small box that we tested a couple, 3 years ago to prove that the concept could take pressure and would meet the design constraints. We went from there to assembling this piece of 30-foot structure that we're going to test in the Langley Combined Loads Test System down the street here. So a long effort that has gone into this with NASA and Boeing, culminating in the delivery of this 10,000-pound piece of aircraft structure. We'll stick it into the facility, we'll mount it, it'll be eventually pressurized to various pressure readings. The idea is to twist and turn the part to see if it'll sustain the design loads that would be needed if we were to build a real airplane out of this.
This facility will prove to be a valuable tool for researchers. These types of tests will help in investigating damage tolerance and any repair techniques that may be applicable. One of the key test points that will be addressed in this round of testing will see how Perseus handles routine damage that might be expected, such as a technician dropping a hammer. Researchers need to understand how this new material will react if minor damage occurs. To do this, a unique test rig has been designed by hand. Here is Andrew Lovejoy to explain.
So some of the things that could impact the plane are rocks or debris that's on the runway when it's taking off or landing. As I said, you could have mechanics that could hit it with a tool, or a vehicle driving by could hit it. And all those types of things can cause damage. And on the exterior, you're more likely to have a higher energy because a vehicle hitting it or something being thrown up by the tire is going to be a much higher velocity than, say, a tool drop. So barely visible impact, if you're doing walk-around inspection, it's a damage that you would barely be able to see. So if you're at that level, the aircraft has to be able to sustain the loads that it would normally see, even with that damage in place. So you have to be able to analyze and then test to make sure that you can hold those loads. So what you have to do is an impact test. So we're doing an impact test, and if you were going to impact at the top on something, you would just have a free-falling, you could have a free-falling weight that would come down and hit. And that's fairly straightforward because you have a mass and you have a height, so you can have a straightforward calculation of the energy. If you wanted to hit on the side, we have spring-loaded, but for the multi-bay box, one of the things we're doing is hitting on the keel, which is the bottom. So we have to have an impact that's going upwards. There's very limited space in Colts. You can have an air-driven projectile, you could have a spring-loaded, but those to me are less controllable. So instead came up with the roller coaster impactor. So it's really a controlled drop. It comes down the track and then it'll go up, and when it hits, it's going in a vertical direction. So in order to impact on the keel, we needed the impact weight to go up, and we didn't have any device to be able to do that. So from scratch, we designed and built the roller coaster impactor. The second main part is the track itself. The track itself is to control it and make it go where we want it to go. When it's rolling down, gravity's keeping it on the track. When it starts to go vertical, it wants to flop. So there's actually two pieces of track that will encapsulate this right before impact to guarantee that we're getting that vertical impact on the bottom of the keel.
Numerous tests were performed in the Colts facility to check the box's ability to meet what engineers call the design limit load and the design ultimate load. In aerospace engineering, the term design limit load refers to the maximum load factor authorized in flight. It is extremely unlikely that an aircraft will ever reach this limit during its lifetime. The design ultimate load goes beyond that and is the amount of load applied which will make the component fail. In this case, the ultimate load factor is 1.5 times more than the limit load. With testing and data acquisition complete, researchers found the Perseus box performed beautifully under extremely stressful conditions. It actually performed above the expected design ultimate load factor, which means the box is even stronger than predicted. With that type of result, researchers feel there is an opportunity to lighten the box even more, potentially making future aircraft even more efficient. Although this stage of the testing is complete, the team has reams of data to look over and will continue working to make the aircraft of tomorrow stronger and more efficient than ever. The hinged wing design on aircraft has been around since the early 1900s. Currently, this design is state-of-the-art and almost magical in its operation, extending and retracting during takeoff and landing. But hinged flaps have drawbacks, such as high noise levels, and their design affects the flow over the wing, making them less efficient. NASA is currently working on improving specific aspects of wing design and has partnered with a small company out of Ann Arbor, Michigan called Flexus to combat these problems. Their innovative design has the potential to revolutionize flight by having the wings on aircraft act more like a bird's wing rather than the traditional flap system we have now. Here is Dr. Sridhar Kota, the inventor of the Flexus wing, to explain.
So with the current flaps, once they're tucked in, you don't want to move those flaps because the flow will separate. So the aerospace community has known for a long time that if you have a seamless wing that can be morphed in flight to maximize the performance, then you can get significant fuel efficiency. And actually, Wright brothers did that for roll control.
The idea to have aircraft wings morph is not a new idea. In fact, the Wright brothers' first designs used morphing wings to help with controlling flight. But as aircraft became heavier and began using stronger materials, aircraft designers were forced to stop using the morphing wing technique and use flaps and slats, which have been in use ever since. Designers have long known that reducing the use of flaps and going back to a morphing wing would be more efficient, but until now, no one was quite sure how to make it happen. While looking at this problem in the early 90s, Dr. Kota came up with an idea called compliant design that uses techniques that are borrowed more from nature than from traditional mechanical designs.
Everything we engineered, if you look around the objects around you, anything that is strong is also very rigid. And when you want mechanical functionality in the design, you put multiple parts, springs, cams, gears, and make intricate mechanism that works beautifully. Whereas designs in nature are different. They are strong, but they are compliant. They're flexible. So you can see the trees bending in heavy winds, so they bend rather than break. And you can see countless examples in nature where you get pretty intricate mechanical motion without conventional joints. And in fact, 80% of living creatures are invertebrates, and they do pretty well with the locomotion and other mechanical functionality without multiple joints and links. So the question is, how do we capture that, where we want a monolithic structure that can do mechanical motions without joints? So the idea is that how do we get this compliance, the flexibility distributed throughout the structure, and how do you design structures like that? So I'll give you a simple example of what I call the distributed compliance. And you can see this here. So here, this can be a monolithic design, no joints. And when I apply force at these tabs, and you can see it move, so you can get large deformation. But the way it's designed is you have very small stress in the structure, which means every section of the material shares the functionality, shares the load, so the stresses are evenly distributed. that's how we have very small stress, very small strain. It works in a linear elastic strain region, so you get large deformation, and which means you can do this multiple times. You can do this millions of cycles and still not fail.
Although the exact technique is still a trade secret, the Flexus team's design uses a proprietary algorithm in a way that minimizes the force it takes to morph the wing to a prescribed shape. This technique also has inherent mechanical advantages in that it is very stiff to external loads. Simply put, the design is incredibly strong, but does not need huge motors to morph the wing. To test this concept further, NASA's ERA team decided to place a Flexus wing on board an aircraft to test in flight. The team removed the traditional flaps from a Gulfstream aircraft and replaced them with a Flexus wing for the initial testing. Tom Rigney of NASA Armstrong explains.
The reason it's important is because one of the contributors of noise, one of the largest contributors of noise for an aircraft, when it comes down to approach for landing or for takeoff, there's a lot of noise that's generated by the spaces and gaps from existing flaps that are on an aircraft. And so what this does is it reduces that noise by eliminating those gaps. And they have a smooth, continuous surface rather than having gaps. And it can reduce sound within up to 4 to 6 decibels, which is significant. This technology is really helping aviation, the whole aviation industry. It's something similar to what we had with winglets. So winglets came on aircraft and made them much lighter and more efficient, more effective. And this is similar to winglets. We're going to be able to take an airplane and have wings act more like a bird. Instead of having just these boards that come down and all locked in place, we're actually have morphing and shaping wings just like a bird would do. And that makes the aircraft more effective in terms of flying, in terms of efficiency, fuel savings, and it's going to save hundreds of millions of dollars for the public for flying. It's also going to make planes lighter weight, which allow for more luggage and other things to go on board. And it's more of a green type of technology, less carbon in the air for the world to have to deal with later. So this is going to be really helping out the environment as well as saving money. So it's really a great technology.
The first tests of this design were very successful and met all of the stringent stretch goals that engineers set out to meet. This design shows tremendous promise, and future testing should continue to further validate the time and effort that the ERA team put into this technology. NASA, in cooperation with industry partners, is truly transforming the concept of how we fly. 2025 is right around the corner, and before you know it, many of the concepts the ERA team has studied will undoubtedly be used to make flying safer for all of us.
Hey, NASA astronaut Reed Wiseman.
Hey.
Do you think you have a few minutes to answer everything about living in space?
I got all the time in the world.
Awesome. Well, where are we?
We are in the Space Vehicle Mock-Up Facility. It's a gigantic building at the Johnson Space Center in Houston, Texas. And this is where astronauts spend the bulk of their time training for spaceflight.
Is this the window where you took all those really cool pictures of Earth?
This is the cupola. It's a series of 7 windows that look down on the Earth.
Nice. How big is the International Space Station?
They say it's about the size of a 5-bedroom house. It's kind of hard for me to conceptualize. In reality, it's just really narrow and really long.
How long did you have to train before going to the ISS?
About 5 years.
And how many total days have you spent in space?
165.
What's the record?
Jeff Williams, he has the US record, 534 days in space, but Russian cosmonaut Gennady Padalka, almost 1,000.
Wow, what's a groundbreaking experiment that you completed aboard the ISS?
I survived.
I heard you age faster in space.
Maybe a little bit.
Is there a maximum height or age that you have to be to become an astronaut?
We used to have restrictions on that, but now it's pretty much come one, come all.
Is there Wi-Fi?
There is, but it's not as good as it is on Earth.
How do you get in contact with people on the ground?
We have space-to-ground communication systems. It's basically a radio or a walkie-talkie, and we just call on this and say hi to Houston.
Is there a delay?
Almost none.
How did you get to the station?
A rocket.
How long did it take for you to get from Earth to the space station?
Takes about 6 hours.
And how long did it take for you to get back?
Oh, that's a crazy ride. It's about 3 hours long.
Any jet lag?
Horrible jet lag.
How often do you get to talk to your family?
Get to talk to them once a week.
Ever prank call anyone?
Of course you prank call people.
Ever get homesick?
Yeah, you get homesick a little bit.
So are the beds comfy?
There are no beds.
I heard you have to be strapped to a wall.
You do?
Are you claustrophobic?
A little bit.
What else can you do in your room besides sleep?
You can read, watch TV, do some work, whatever you want.
Do you have a bedtime?
Everybody has a bedtime.
Do you have alarm clocks?
I use my watch.
How many crew members do you have?
It was me and 5 others.
Were there any language barriers?
Doc and Yeshna, of course there were language barriers.
Ever get sick of your roommates?
No, you never get sick of your roommates.
What did you do in your free time?
Oh, you look out the window.
What's a typical breakfast aboard the space station?
It was very much like a breakfast on Earth, so I liked eggs, occasional oatmeal, maybe even a waffle.
Was the food any good?
I actually thought the food was pretty good.
What's your favorite meal on the station?
I love chocolate pudding cake.
How do you cook your food?
You can either inject it with hot water or put it in a food warmer.
What's the first thing that you ate when you got back to Earth?
I really wanted a pizza, but I saw a salad and went for it.
So did you have to work out?
You work out twice a day for about 2.5 hours, 2.5 hours.
And what kinds of exercises?
Primarily, you're either lifting weights or running on the treadmill. Our treadmill is attached to the wall, and so when you're on it, you're running straight down towards Earth. Very weird feeling.
So how do you stay on the treadmill without floating away?
Bungee cords.
So do you burn the same amount of calories as you do on Earth?
I think you burn a little bit more because your brain is always active.
I heard that in microgravity, sweat sticks to you.
It does. If you have hair, it kind of builds up in your hair and you get this big sweat bubble on your head.
How do you shower?
We have soap impregnated towels.
How do you pee in space?
Ooh. We have a funnel.
Where does your pee go after you flush?
A little bit of processing and then right back into the drinking water.
How do you pee in a spacesuit?
We have a diaper.
How much water do you have to drink each day?
You drink just about the same that you would on Earth.
Do you ever run out of anything?
Free time.
How do you get more supplies?
We have cargo ships. We have great companies like SpaceX, Orbital. We have Russian resupply vehicles and also Japanese HTV spacecraft.
What'd you miss most on Earth?
Oh, my wife and kids.
What personal items did you take with you?
Photos of my wife and kids.
Did you bring any space souvenirs home?
You always have to bring souvenirs home for your kids.
So I have to ask, what's your favorite planet?
Oh, it used to be Saturn until I saw Earth from space.
And if you were to travel anywhere in the solar system, where would you go?
I work at NASA. We all want to go to Mars.
Does the space station ever get too hot or too cold?
Oh, we keep it a balmy 72 all year round.
Nice. How about the temperature of space?
Plus 200F to minus 200F.
What about the temperature inside the spacesuit?
It's actually pretty warm, pretty nice, pretty comfortable because there's many layers of thermal protection.
How much does a spacesuit weigh?
Oh, it's really heavy. I think it's about 300 pounds.
How do you do your laundry?
We throw it out.
Do you have to clean the spacesuits?
Of course you got to clean the spacesuits, especially after a spacewalk.
How long does it take for you to put on a spacesuit?
About 45 minutes.
Can you put it on by yourself?
If you're in a pinch, you can put it on by yourself.
How long does a spacewalk normally take?
We train for about 6.5 hours.
And what's the max amount of time a spacewalk can last?
The maximum is about 9 hours. I think 8 hours and 54 minutes is our record.
How's the view?
Awesome.
What's the hardest thing about a spacewalk?
Just knowing that you're outside, and if you mess anything up, you've destroyed a $100 billion spacecraft.
And what's the most rewarding?
Coming back.
Sounds awesome. Well, I'm sure there are a lot more questions, but I know you're busy, so we'll save those for another time.
Sounds good.
Awesome. Thanks. Have a good one.
See ya.
closeout crew is not special. There's thousands of people out here that have thousands of jobs, you know, and each one's equally important. The only unique thing about us is we have the last hands-on job before the bird flies.
The closeout crew is the last to shake the gloved hands of Space Shuttle astronauts before they rocket into orbit from NASA's Kennedy Space Center in Florida.
We close the vehicle out for flight, which means we take out anything that doesn't fly. We put in what needs to fly. We put the astronauts in, strap them in, and we close the hatch for flight.
The team is made up of NASA and United Space Alliance workers from Kennedy and the Johnson Space Center in Houston. The Orbiter Closeout Crew Chief coordinates launch day activities and communicates with the firing room via radio. He goes by the call sign OVCC. 2 technicians are experts at the shuttle crew module side hatch, and 2 insertion technicians specialize in helping the astronauts strap into their seats. An additional astronaut joins the closeout crew as the Prime Astronaut Support Person with the call sign ASP. A NASA quality representative rounds out the team.
We got 3 tenths and 3 tenths.
20 people are certified to work with the closeout crew, but only a few serve at a time.
So on launch day, we all come together to make one team. There's only 7 people out of that 20 that would support a launch, come up here as a prime team.
It all happens at the 195-foot level of the shuttle launch pad, where the orbiter access arm leads to the climate-controlled White Room. The closeout crew reports to the launch pad shortly after the shuttle's external fuel tank is filled with propellant several hours before launch. The team sets up its own rescue gear and takes care of some pre-boarding housekeeping duties. Then the astronauts arrive, and suddenly the White Room gets a whole lot more crowded.
Okay, once the crew gets here, naturally I can't put all 7 people in, or 6 or 7 in the ship at one time.
The countdown allows 50 minutes to get everyone strapped in with their gloves and helmets on. The astronauts need help putting on their parachute harness and communications gear before climbing aboard. After a round of communications checks, anything not needed for flight has to come out, including the closeout crew.
All right, gotta go to close the hatch. So we go and close the hatch, pressurize the cabin, do some last minute things. It takes us roughly an hour after we close the hatch to get out of here.
But before they go, the White Room must be partially taken apart so it can swing back into position beside the shuttle if there's an emergency, even if the astronauts have already opened the hatch.
You can see these billows behind me. We deflate those, and this White Room has hinges, and so we would swing one door out, swing this piece, comes this way. So there's a big gaping hole right here.
When everything is cleaned up and strapped down, it's time for the closeout crew to leave the astronauts alone at the launch pad. They've got it down to a science, but with so many tasks involving so many pieces of shuttle and ground hardware, things don't always go according to plan. From burned out light bulbs on cockpit switches to problems with the hatch, the closeout crew has seen it all and had to fix it fast. So they bring 2 boxes of tools to the White Room, with even more in their truck down by the elevator.
You know, you can't always think of everything, but these guys are very good at improvising.
When the shuttle is fully loaded and ready to fly, everyone in or near the vehicle is working in a hazardous area. The closeout crew and the astronauts practice escaping the launch pad in case there's ever an emergency. Everyone has to learn how to move from the White Room to the slide wire baskets that would whisk them away from the pad down to a nearby bunker. In an emergency, a series of overhead sprinklers called the Firex system would activate and lights would come on, showing everyone on the 195-foot level the way out.
So we have this painted yellow with black chevrons. We call it the yellow brick road, and that's because you basically can't see anything but your feet. So you follow the chevrons out to your primary egress route to the slide wire baskets.
One of the benefits to being part of the closeout crew is working closely with the astronauts.
It's a unique gift, I think, that we get to know them personally. We get to shake their hand right before they go in. Some of the astronauts that are on the closeout crew actually fly. So, you know, one time supporting a mission, they'll be wearing a white uniform with us, and the next time they'll be wearing an orange uniform getting ready to fly themselves.
As the program draws to a close, many Space Shuttle team members are making the most of the final flights. And that, of course, includes the closeout crew.
And I'll probably just stand over there in the corner and soak it in, try and remember as much as I can, and hope that another program comes along and I get to do this again.
Even astronauts need a place to stay before they rocket into space. The crews of the Space Shuttle launching from Kennedy Space Center in Florida, that place was the astronaut crew quarters, a set of bedrooms, offices, and facilities built into the center's operations and checkout building. Resembling a college dorm, the crew quarters doesn't scream technology in space as much as it whispers comfort and familiarity. And that's the idea. Give the astronauts a place to relax, eat, and sleep before they go to work in space on missions that will mark some of the most taxing times in their lives.
My first impression when I arrived was, wow, I'm in astronaut crew quarters. I mean, you walk in, it was before it had been remodeled on my first flight, and these are the rooms that the Apollo astronauts stayed in. There's nothing fancy about it, you know, it's not going to the Ritz-Carlton. It wasn't even a Motel 6, but it was astronaut crew quarters, and that was really special.
Gemini astronauts were the first to stay in the crew quarters. All the Apollo astronauts slept here before going to the moon. The facility grew when the space shuttles began taking more and more people into space at a time. The aura of crew quarters grew with each landing and each new spaceflight achievement, even among the astronauts. A couple of the rooms were seen publicly on launch day, but most of it remained a mystery until the shuttle's retirement. Kennedy Space Center Director Bob Cabana, a former astronaut who spent many nights in crew quarters preparing for his missions or helping others get ready for theirs, showed off some of the lesser-known areas of the facility, along with the spots that are familiar to space program enthusiasts.
The dining room, what you guys probably remember seeing all the time, is, you know, the crew's sitting at the table, and they're all smiling, and everybody's, you know, up and ready for launch, and they're in their crew shirts, and you know, they take general shots of everybody, and then they move off, and then the crew actually sits down and eats.
The cooks at crew quarters have to accommodate a range of tastes, keeping in mind that astronauts are often concerned about how their stomachs will behave once they get into weightlessness.
I'll never forget my first flight. We're sitting around the table, and one of my crew members who it's his first flight, and after the cameras all left, he's got steak and eggs and hash browns and coffee, and he's pouring hot sauce on, and my commander looks over and he says, going for color and distance, I see.
Like the rest of the facilities in crew quarters, the bedrooms are not extravagant, but they work.
It's a very small room. You got a desk, a bed, and a shower and a toilet in the bathroom. Very sparse, but very functional. It's very quiet. It's an elevated floor back here with sound insulation underneath, sound insulation up above, and so crews that are on weird schedules can actually come in here and get some sleep.
But a quiet room doesn't always do the trick when a launch is waiting the next day.
It's not anxious, it's just you want to get off and do it. And in fact, one of the hardest things, some folks really like coming down to crew quarters and just relaxing a little bit before they fly. And I came down and it was like, I want to launch. We're here, let's launch tomorrow, you know, but you can't do that right away.
A new conference room was built to accommodate the larger crews of the shuttle and International Space Station, including foreign crew members.
This is where they go over all the flight data file, get any changes, updates. They get the weather brief on the screens here. It's a place to come and relax. We have simulators that simulate robotic arm operations for both shuttle and station, as well as a simulator that lets you actually land the space shuttle. And it's a pretty good simulation.
Space is a lousy place to get sick, so specially trained doctors and nurses, along with exam rooms, are on hand to make sure everyone stays well before heading into orbit.
Pre and post launch, there's examinations that have to be done. You got to see the doc. You know, if anybody got sick while they were in crew quarters, they go see the flight doc. and just make sure it's those last-minute checks that everything's okay. And it's just their standard small exam rooms and a private place to meet with the doctor when you're here.
A staff is on hand to take care of all the aspects of an astronaut cruise day, from housekeeping to scheduling.
The people down here are family. They really get to know you. The folks that run crew quarters, that keep it clean, that cook for you. I mean, there are friends that I've made for life and have bonded with from my time down here.
As much as the crew quarters is set up to mirror everyday life, there are rooms that are meant solely for the unique demands of going into space.
All right, and of course you guys have seen this on TV hundreds of times. This is the suit room where the crew gets suited up to actually go fly in space. You're tight with the suit techs that are working with you, and it's that last, hey, we're getting ready to go fly in space. This is really, it's a big deal. It's kind of neat.
There's also a launch day tradition that plays out in this room.
Probably the biggest tradition is the game Fargo Possum. And Fargo Possum is low-handed poker. And the rule is you can't leave crew quarters and go to launch until the commander wins the hand, has the lowest hand, and that sometimes takes a while.
All right, you can fly!
Now suited for space and following several days at crew quarters, the astronauts get to take a walk through the corridor to the elevator that will take them to the waiting Astrovan and out to the launch pad. Cabana served as the flight operations director during a number of shuttle missions, watching over the astronauts as they prepared to head into orbit. His advice to flyers was pretty simple. Let it sink in.
Mostly what I tell first-time flyers is, when you get ready and you're up in space and you have a free minute, make a memory. Stick your nose up to a window and make a memory, because the eyes God gave you are so much better than any camera. And when you look at a camera picture when you get home, you're disappointed. It's just not as vibrant, it's not as real as it is when you just look out the window and make a memory.
The space shuttle could get all the way to space on its own power whenever it launched from NASA's Kennedy Space Center in Florida. But when a shuttle orbiter travels from one place to another here on Earth, it needs a lift, a piggyback ride or ferry flight aboard the shuttle carrier aircraft. It's an unusual sight, a low-flying jumbo jet with a spaceship bolted onto its back.
And it's really amazing to see, first the orbiter in person. It's almost surreal.
The shuttle carrier aircraft is actually a Boeing 747, modified to handle the weight and drag of the shuttle orbiter on its back. It's been supporting the Space Shuttle program ever since the approach and landing tests during the late 1970s. In 1990, NASA added an additional modified 747 to its SCA fleet to make a total of 2 aircraft available for ferry flights. The shuttles began all their space careers with ferry flights when they were first delivered to Kennedy from the manufacturing plant in Palmdale, California. But most of the time, a ferry flight was needed to bring a shuttle back from Edwards Air Force Base in California, following a landing on the West Coast due to poor weather in Florida.
They built the 747. They built a very nice airplane, and it does what you want when you fly it. The only thing that's different is when you're carrying the orbiter, there is a noticeable vibration, and of course the speeds are quite a bit higher. But as far as the feel in the aircraft and the ease with which the aircraft flies, it is deceptively easy.
After an end-of-mission landing at Edwards, it took the landing team about a week, weather permitting, to prepare it for its upcoming cross-country trip. A tail cone was installed to reduce aerodynamic drag and turbulence during the ferry flight. The spacecraft was lifted inside a large gantry-like device called the mate-demate device. The aircraft rolled underneath, and the orbiter was lowered and bolted into place. The team simply reversed the process to remove the shuttle from the plane. Sometimes just getting the shuttle and aircraft ready for the trip could be a test in itself. NASA Flow Director Stephanie Stilson recalls the challenges the ferry flight team encountered in 2005 after Space Shuttle Discovery landed at Edwards at the end of the return-to-flight mission STS-114.
And everybody thinks the desert, dry, no issues, no rain. Well, we had snow in the mountains, we had rain, we had lightning that actually struck the mate-demate device, and we had locusts. So it was like everything that could possibly happen outside of our control happened. But once again, that just gave us a chance to show how we can react to changes and things that we're not expecting.
But the toughest part of a ferry flight is keeping the shuttle safe from harmful weather or other conditions during flight. So, a Pathfinder aircraft flies 100 miles ahead of the attached pair, making sure the flight path is safe and dry.
You don't want to bring it through any turbulence, no visible moisture. There's some temperature limitations. And essentially we're the plane to make sure we don't bring the orbiter through there. So our job is to be very vigilant of any changing weather conditions and to make sure that the orbiter is brought on a safe flight path.
There were 87 ferry flights throughout the Space Shuttle program, including flights for testing, delivery, orbiter upgrades, and of course, end-of-mission landings. Today, the shuttles are being prepared at Kennedy to go on public display at sites across the country. Atlantis won't need an aircraft to move to its new home at the Kennedy Space Center Visitor Complex. But Discovery, Endeavour, and the test orbiter Enterprise will each take one last ride. Discovery will be flown to Dulles International Airport in Virginia and then moved to the nearby Smithsonian Udvar Hazy Center. It will take the place of Enterprise, which will be flown from there to John F. Kennedy International Airport, and then on to the Intrepid Air, Sea, and Space Museum in New York City. Endeavour will be flown to Los Angeles International Airport before making its way to the California Science Center in Los Angeles. The bulky combination of orbiter and aircraft is unmistakable and usually attracts attention from onlookers on the ground as it makes its way across the sky. NASA plans to keep one of the modified 747s for its Stratospheric Observatory for Infrared Astronomy, or SOFIA, science program. But as the shuttles make their final ferry flights, space fans along the way may be able to catch a glimpse of the duo making one more pass overhead.
And so that's a great thing to be able to do that. And then if we have any stops along the way, it's a chance for us to share the orbiter with the public in that area that most likely has never even seen a space shuttle that close.
It takes hundreds of controllers to orchestrate a space shuttle launch. Their office on launch day is one of the most unique workplaces in the world, a firing room at NASA's Kennedy Space Center in Florida. The firing room serves as the nerve center on launch day.
KC Safety Mission Assurance. KC Safety Mission Assurance will go, Mike. Thank you, Mark.
Behind consoles, wearing headsets and checking off countdown milestones in thick binders, launch specialists monitor the space shuttle as it stands at the launch pad 3 miles away. From the firing room, they also send commands to the spacecraft, talk to the astronauts, and communicate with dozens of other teams, from rescuers near the launch pad to mission controllers in Houston. A successful countdown and launch requires the team to complete more than 1,600 steps in order. The checklist is contained in part of the 8-volume set of shuttle launch documentation. Covering almost 8,000 pages, the books also contain contingency plans for handling launch scrubs or emergencies.
Range weather.
Weather is green on all constraints. Winds are from 335 degrees, 18 to 25.
Okay, thank you, Kathy.
Keeping track of the countdown as a whole are the Shuttle Launch Director and the NASA Test Directors, or NTDs. They sit in the front of the firing room at consoles on risers. The orbiter test conductors share the second row with the NTDs. In the back of the firing room, facing the 2-story window looking out at the pads, are a series of horseshoe-shaped cabinets. System specialists sit there. They have a deep knowledge of the inner workings of the space shuttle. If a problem crops up, they are the ones who would bring it to the attention of the people in the front of the room. The specialists also would be called on to come up with solutions to allow a safe liftoff and present them to the launch team. NASA built space for 4 firing rooms on the upper floors of the Launch Control Center at Kennedy during the Apollo program. Each one is dominated by the angled panes of glass that let controllers inside see the spacecraft on the pad and during the first minutes of ascent. When the first Space Shuttle mission launched on April 12, 1981, controllers in Firing Room 1 had the primary responsibility for the liftoff. The firing room recently was renamed the Young Crippen Firing Room for that first crew. Firing Rooms 2 and 3 also were equipped and staffed. Shuttle launches require 2 active firing rooms, one as the primary and one with senior engineering and management personnel teams. A third firing room is capable of stepping in. Firing Room 4, which had been a conference room during much of the shuttle program, was remodeled and opened in 2005 to give the launch team more room and modern computers. The computers are used to constantly monitor the shuttle's myriad of systems. Simply put, they can pick up minute changes in a system's status before a human could detect it. Late in the launch countdown, the computers run the countdown completely through a set of software called the Ground Launch Sequencer.
We're ready to go.
Thank you very much, Scorch. Appreciate that. NTD, with that, you are clear to launch Atlantis.
Copy. Clear to launch.
The launch control team can intervene to hold a countdown if they see something they don't like, but otherwise, it's the software that retracts the orbiter access arm, the gaseous oxygen vent hood, and commands the Space Shuttle's 3 main engines to ignite.
Roger, roll.
Beautiful sight.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, and I always say, I don't think ever. I think NASA, they realizes that they have 2 marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, The goal was to do that to hold up for decades, and apparently it's still, it's got better legs today than it did then.
Ignition sequence start.
Good morning, and welcome to this view of the International Space Station Flight Control Room. This team of specialists you see here is keeping an eye on the station's systems and is working with the members of the Expedition 64 crew as they kick off their 6-month mission. That's right, Commander Sergei Ryzhikov and flight engineers Kate Rubins and Sergei Kudzverchkov said goodbye to 3 crewmates this week and kicked off their own mission of scientific investigation, which is scheduled to last into April of next year.
Houston Station on Space to Ground.
Welcome to Space to Ground. I'm Isidro Reyna. This week marks the beginning of Expedition 64. 2 veteran International Space Station crew members swapped command of the orbiting laboratory during a traditional change of command ceremony on October 20th. The 6-member space station crew gathered together when Expedition 63 Commander Chris Cassidy of NASA ceremonially handed control of the station to Expedition 64 cosmonaut Sergei Ryzhikov of Roscosmos.
We have this small tradition where there's a key to the International Space Station. It's a tool that we use on the Russian hatches to open and close the hatches. And it symbolizes the camaraderie that we have between all of the space agencies. And Sergei, it's with great pleasure and honor that I present you this key and command of the International Space Station. Congratulations.
Ryzhikov officially began his command on October 21st when Cassidy and flight engineers Anatoly Ivanishin and Ivan Wagner undocked from the station. The crew undocked from the Poisk module inside the Soyuz MS-16 cruise ship, re-entered the Earth's atmosphere just over 3 hours later, and parachuted to a landing in Kazakhstan, bringing their 196-day space mission to an end. This week's question comes from Ridgedale Middle School. Students want to know if astronauts ever experience a language barrier while on board the International Space Station. A truly global endeavor, the unique microgravity laboratory has hosted 240 people from 19 countries, almost 3,000 experiments from over 4,200 researchers in more than 100 countries, and a variety of international and commercial spacecraft. Differences of nationality and culture, as well as being isolated for months at a time on the International Space Station, can be demanding. Before astronauts travel into space, they are briefed on the cultural differences they may encounter with crew members from other countries. While English is the primary language spoken aboard the station, crews must also be proficient in the Russian language. Keep sending in your questions using the hashtag AskNASA. We'll see you next week.
Chris Cassidy's 3rd trip to the International Space Station started last April on a launch pad in Kazakhstan and wrapped up a 6-month mission filled with milestones for space exploration, plus all his work on science experiments helping benefit life back here on Earth. Here's a quick look at some of the science he enabled during his research-filled stay aboard the world-class laboratory in low Earth orbit.
A lot of science going on today. We got me doing biomole, Doug doing astrobeat. So the scientific team is in California. The payload control center is in Huntsville, and of course I'm here. Pretty cool stuff.
Station Huntsville, Space to Ground 2 for Chris and Cryochiller.
Recording in the name of science. Fecal processing complete. We're working with foam, and this is the FSO. Let's go for it.
And just make sure that the liquid is in the bottom of the tube. You can just do that by giving it a flick of your wrist.
I think all of the things we're working on are applicable not only to life in space, but translate to Earth in some way. We're certainly working on life support systems on the International Space Station that will help keep crews safe as they go beyond low Earth orbit. And that can translate to health systems on Earth as well. It's a really robust science program that we have up here, and I think you'll find a lot of benefits coming back to Earth.
busy day of science on board the International Space Station.
Expedition 64 flight engineer Kate Rubins is both a scientist and a NASA astronaut, and there's no better place to be for someone with those two job titles than aboard the International Space Station. The microbiologist says being free from Earth's gravity makes this outpost the perfect place to conduct research.
The reason that you would do any kind of experiment in space is if there's something particular about the space environment, and most often that is microgravity. So mostly the ISS gives us the ability to either do something that we can't do in a facility on Earth or investigate some phenomenon, some property in a way that we can't on Earth. So for example, some of the tissue architecture, these really delicate tissues, as you start to build them up, they would collapse because you have gravity, or the cells would naturally settle to the bottom of the plate. And so you just can't study the answer to the question that you're looking for. So the space station lets us have that ability to either test what the effect of gravity is or remove that problem entirely from our experimental setup. Yeah, the space station's an incredible place to conduct research. It was sort of like being in the world's most amazing lab when I was up there in 2016. So when you're a scientist, you're used to working on one thing over and over and maybe really refining the details on that over the course of a PhD thesis or a lab project. On Space Station, you get somebody's incredibly refined project times 200 different fields. So for me, it was a chance to learn about all these different areas of science, and they each have a team behind them. So I was usually pretty excited to open the container and do whatever experiment that day brought. I also really got a chance to talk to those PIs, the principal investigators, and the scientific teams, and understand everything that was going on behind their experiments and read their papers. So by the time I got to doing the experiment, I was pretty excited to take it out and to see what was going to change in microgravity. Yeah, science in space, it's an amazing lab and it's incredibly fun. So we are smiling all the time. I'm Kate Rubins. I'm a scientist and an astronaut.
You can't do exploration from inside of a spaceship looking out a window. We really need the astronauts to go out and do exploration.
And so we are trying to provide the best tool to the crew members that we can, no matter where they go. So it's the exploration spacesuit.
This new suit allows the human to move more naturally and more fluidly. The system will adapt to the human inside it, and the human will adapt to the system.
It is like a brand new spacecraft.
Even has the new smell and everything.
It does. New car smell.
It's very exciting. My career happens to coincide with this great opportunity to go back to the moon. Like, I can't believe I'm so lucky just to be here at this time.
The laboratories of the International Space Station provide a home for dozens of experiments at a time in a wide range of scientific disciplines. But the outside of the space station supports science research too. There's a great big experiment out on the starboard truss that was recently put back into service after a series of spacewalks, getting it back to work searching for cosmic particles which originated billions of light years away, and which may hold the key to the origin and composition of the universe.
Humans have observed many wonders across the cosmos, yet much of our universe is still shrouded in mystery. Among those mysteries is the formation of our universe, which should have resulted in a balance of matter and its corresponding counterpart, antimatter. Much of that matter is thought to exist in the form of dark matter, which can't be directly observed. Much of the antimatter can't be found at all. Studying